right, let me get started. So first of all, thank you for inviting me to talk about the STAR time of flight detectors. I realized that doing this, it's been almost to the day 10 years ago that I talked to juniors about the time of flight detectors as well. So a lot of them moved on. But I also realized when looking into the time of flight detector that a lot of things that going back, it was quite interesting to see all the developments. So what I'm going to talk about here is a brief outline. I'll talk a little bit about particle identification, the TOF detectors in STAR, do a very brief primer on what these Mrpcs are all about, and then focus more on the detectors that we have here in STAR and some of the aspects that come with the calibration and analysis of the data of these detectors. So kind of, just to kind of get everybody on the same place here, time of flight particle identification is, let me get my, so that's better. So time of flight particle identification. So the whole idea really is here to calculate the mass of the particle, and I hope you can see my mouse move a little bit, by measuring the momentum, which is determined by the TPC, the path length, which is also determined by the TPC, and the elapsed time, which is what the time of flight detector is supposed to provide. You all know how that looks like. I think what's important to realize is how accurately can we measure this mass, or in this case, the mass squared. And so what you can see here is that the relative accuracy with which we can determine the mass squared is given by the TPC momentum resolution, as well as the time resolution and sort of what we call the pointing resolution, or just the accuracy with which you can do the path length determination. And you can see that it really is a gamma factor here that makes the time resolution really matter in our particle identification. And typically the plots that I'm sure you've seen in some of the updates that are given at physics working groups, they typically look like this, where the mass squared plot as a function of momentum show this typical development where as the momentum increases, you can actually see these bands blow up a little bit, which is the combination of indeed a change in momentum resolution yeah. So okay, yeah. Instead of doing PID based on m squared, you can also use 1 over beta, and 1 over beta is one that makes the resolution somewhat more clear, that it depends on the time resolution and the path length. And it also makes it somewhat easier to make cuts, because if you look at the previous slide, you can see that you have to make cuts that kind of take care of the changing momentum resolution as well. Whereas if you look at 1 over beta, you in principle can make somewhat cleaner cuts by using the 1 over beta that you measure minus the 1 over beta that you expect. So here you explicitly put in what the mass of a particle is and look for this particular distribution to be centered around 0, and the width is given by the resolution, which again is given by the time resolution. Now, you have to be a little bit careful, because really the resolution in 1 over beta also still includes the TPC momentum resolution, which is really something that if you are looking at heavier particles, in other words, if you're looking at protons, you need to be a little bit more careful, as you can see in this plot right here below. To put this in kind of to understand what the effects are of time resolution on the performance of your particle identification, I'm going to give you an example here. And this graph may look a little bit complicated, but let's kind of walk through this. Let's just assume that we have a time resolution of about 100 picoseconds. Take some typical assumptions on what the momentum resolution and this pointing resolution is. And then you plot that 1 sigma mass resolution that I showed on the first slide as a function of momentum. And let's just take the pion here as an example, and you can see indeed that given 100 picoseconds, that you will see that this 1 sigma band for short tracks, these are the straight lines, versus longer tracks, which is eta going to, more to the 1. There you have somewhat less of a sigma because the tracks are longer, and so you get a better determination of your 1 over beta. And you can see here that this band starts to blow up as you increase in momentum, and at some point starts to overlap with that of the kaons that overlap. And then, interestingly, you'll see that even before the kaons get a chance to start to overlap with the protons, this whole pion band already crosses into the proton band, and etc., etc. The point really is here that you can see, and this is for 1 sigma lines, that say at about 1.6 or so GeV is where we can see the, for short tracks, so straight up eta equals 0, that pions and kaons are going to overlap. But again, the time of flight detectors in STAR are there to really kind of push PID from DEDX that the TPC normally does, and which kind of stops already earlier at lower momenta, to higher. So here you can see that the pi kaon separation, at least at a 1 sigma level, goes up to 1.6 to 2 GeV, depending on the length of the tracks. And the protons can still be separated out to somewhere between 2.6 and 3.2, again, depending on the length of the track. And this is for the example of 100 picoseconds. You can also look at it a different way. You can take what I just showed you and now look at where that separation on the vertical axis is as a function of time resolution. And like I said, if we typically look at 100 picoseconds, then you can see here that the pi k separation, again, depending on whether we're looking at short tracks or long tracks, is at about 1.6 or 2. And if you push the time resolution, which you'll hear coming back again and again in this talk, if you push that to lower, you can see how you start to further push the overlap away, where pions and kaons, or pions kaons, start to overlap with protons. And you can see this here as a function of time resolution. Okay. Now, with that in mind, and this is where I realized that this is really a long time ago, more than 20 years ago, there was a letter of intent made, and I'll just quote, highlight here, by Rice and actually several other institutes, I should say, that really wanted to pursue the development of a time of flight capability for the STAR detector. And for that, already some initiatives were developed in using conventional techniques based on scintillators and photomultiplier tubes. And that made really a case that while that time of flight really was a capability that was much to the benefit of the STAR detector, but also it was quickly clear that expanding a scintillator-based detector, time of flight detector, would be extremely costly. And so at about in early 2000, late 1999, the proposal was made to look at these so-called multi-gap resistive plate chambers as a way to, as a different technology to do timing measurements. The result of that is the BTOF detector that you all use. But equally so, we've seen other detectors in STAR appear that also further on that technology, such as the MTD, which is based on Mrpcs, and the end cap time of flight that recently was installed and also uses Mrpc technology. The ALICE experiment uses Mrpcs for that are around their time of flight, around their TPC, and CBM, which is our collaboration for the ETOF detector, also is building a wall of high-rate Mrpc detectors for their time of flight needs. All right, so I went into the picture book because, as I mentioned, there was a TOF-P detector, which was a proof of principle, scintillator based, and then several prototypes. And I couldn't help it but just kind of look up these pictures because when I was a junior, I was actually working on these detectors that were just single tray detectors, basically. So on the left side, you can see the TOF-P detector, where we used one tray, which is actually a tray that was used for the central trigger barrel, the CTB, and we replaced the two large scintillator slats that were in this CTB tray with 41 smaller scintillator slats that were each about 20 centimeters long. You can see them here nicely lined up. We were able to squeeze in 41 scintillators, each read out with their dedicated photomultiplier tube. If you look carefully, these little black cylinders are these photomultiplier tubes. This detector was installed for the 200 GeV run, and we were able to actually get time resolutions that were expected, and we see sort of typically in the order of 80-ish picoseconds, as you can see from this plot that shows for every slat number the time resolutions that we determined. You can see there's a few outliers, but then again, this was a first prototype, and that came also with some thing. For example, you can see a whole block here that clearly were lacking high voltage to give anything. From this TOF-P tray, which showed that it really is, that you can use well-established technology, it was also quickly clear that if you are going to use these scintillators with photomultiplier tubes, these have to be photomultiplier tubes that can operate in a magnetic field. And that means you need to look at so-called mesh dynode type PMTs, and they're expensive. If you would look at about 5,000 of them, you already look at the detectors simply just because of the of these PMTs to be more than $15 million. At least that was 20 years ago. So that was certainly a big motivator to look at alternative technologies. On the right side here on this slide, you can see one tray of TOF-R, and this is a detector, as it already is installed, that is using Mrpcs. This was a prototype Mrpc. It had about 168 channels. In its first years, it was still running on KMAC electronics for all kinds of digitization, and as new runs happened, new electronics got tested. But so this detector here featured for quite a few runs on the East TPC at the other side of the TOF-P detector, and as was shown at a workshop in 2004, this setup was already easy, could already deliver. This was in 2004 using KMAC electronics, pretty good time resolutions in the order of 85 picoseconds. This picture on the right side, you can also see here all the old CTB trays that meanwhile have been replaced because, well, we have now the barrel time of flight. All right, so let me give you a very brief primer on Mrpcs and why they actually are really great timing detectors that basically have retired the idea of using scintillators and photomultiplier tubes for time of flight walls, which was quite common in the 90s, and since then, as CBM can show you, is now really Mrpc based. Basically, if you look at, if I start on the left side, and this was an idea that Santonico raised at the 96 RPC conference. And I'm taking this from really very interesting seminar that Crispin Williams, who's really been at the forefront of this, gave a few years, no, 10 years ago. If you look at a wire in a tube, like streamer tubes or whatever you have this anode in the middle, and the signal that you get here is really dominated by the arrival of the closest electron cluster. And the electric field is this 1/r, so you really see typically a signal that looks like this. And you're interested in the first signal, but it does not necessarily be the strongest of signals. And so this is not really the best way to provide a timing signal, because as we will see later on, for timing signals, you want actually large signals, because there are corrections that's especially if you have lots of small signals play a role. So Santonico said, like, well, what if we are looking at a detector where these avalanches, as opposed to coming one after another, are really available simultaneously? And that was the idea at that time of using this Mrpc detector, where you have a very high electric field, but parallel cathode and anodes. And so if you have some induction pickup pads here, these avalanches are then supposedly starting to immediately result in an induced signal. And so having all these avalanches act in parallel would be a way to get a fast and large signal for timing purposes. That was a neat idea, but it turned out to be somewhat correct, but did put people on the right track. The problem, and I show that here on the right side of this slide, is that actually these avalanches that happen when you have a charged particle going through a gas, they only happen, or ones that are producing detectable signals, I should say, really only happen close to the cathode. They have, we see that mostly the avalanches that are detectable are the ones that really traversed through the whole gas gap. The ones that were produced later on didn't really produce signals that were much detectable. And again, we're looking here at the picocoulomb level. And so what you saw in these Mrpcs is that these clusters were predominantly produced, or the ones that you detected, were predominantly produced close to the cathode. So you could have a 2 millimeter or more gap, but it was in the first 100 or so microns where these detectable avalanches came. Now, you can obviously try to increase the electric field so that all these clusters that you generate are big enough. But at some point you will turn such a Mrpc into the spark chamber that you don't want it to turn into, because these signals have a pretty terrible timing. So how was the question then, which is what really Crispin and others have been working on very hard, how can you get many avalanches to act together? Well, again, first you want to have a high gas gain, but you have to be careful, because you can get now these avalanches to grow large enough that you get these sparks. So a way to stop these growth avalanches is to, well, put in boundaries in this gas, in this Mrpc. So you add these boundaries here on the right plot that are transparent to the fast induced signals, but are resistive. In other words, they will not let the avalanches grow any further. Aha. Well, how does that implementation then look like? And here I show on the left side this so-called multi-gap resistive plate chamber. And so a multi-gap resistive plate chamber really is this stack of equally spaced resistive plates. These are the resistive plates here in yellow hashed. And then we have some signal electrodes on the surfaces that are able to pick up the induced charge. There's a few very interesting features that make this actually a very robust detector that I want to highlight here. And that is that while the cathode and the anode are put to serious high voltages. This is 10, and in star we actually run 14 kilovolts. The internal plates they float. They are not connected to anything, but they will take the correct voltages and will keep those correct voltages as these are resistive plate chambers, as there is a flow of electrons and ions establishing over time. So at some point there is this equilibrium where these plates will each, while floating at first, will take on these voltages. Another thing that is, and so what it means, and I should just say that means that we actually really have in each of these gaps equal gains develop. The other thing is that we have inside each of these gaps, we have that space charge that will build up, and especially in small gaps, we see that will limit the avalanche development. And that is a good thing because we can now push these detectors to longer streamer-free plateaus. Again, streamers are great if you want to build a streamer detector, which happened to be a trigger detector in my thesis. Actually, no, we retired it in an experiment before my thesis experiment. But it's not what we need here for these timing purposes. The idea that the space charge buildup in these small gaps limits the development not only allows us to have these longer streamer-free plateaus as a function of high voltage, but it also loosens, I should say, the mechanical constraints of a gas gap. And that's very interesting. It means that if this resistive layer has some little imperfections, and that, with these significant potential differences, could certainly have some issues there. It is really thanks to that space charge buildup that we don't need to worry too much about small imperfections, and so the constraints of these gas gaps is somewhat loosened. And then the other thing is that we see, I'm moving on to, that was wrong. So, and the other thing is that we see a complete recombination of the positive ions, but also of negative ions, which really, as you get close to the anode side, you'll see that electrons tend to recombine. And but the good thing is that we see that this recombination of positive and negative ions really removes concerns about large currents that may take place in these resistive plates. And this is to the benefit of the rate capabilities that such an Mrpc can have. And you can see that indeed by looking at technologies where you change the resistivity of these intermediate plates, you can actually see further improvements to the rate that such a Mrpc can sustain. All right, how does that translate to the star Mrpc module? The star Mrpc module, it looks like this. It's a size of about 20 by 10 centimeters. We have 6 22 micrometer gas gaps. You can see that here in this side view. To use, since the spacing is important, we actually saw that using fishing line was the best approach to guarantee a standard thickness or a standard gas size of the gas layer, because the production process of fishing lines turns out to be very well controlled, much better than any other spacers that were considered. So a lot of fishing line went into the time of flight detector. We see that we actually use float gas as the resistive plate. Float gas has a bulk resistivity that's something in the order of 10 to the 12 to 10 to the 13 ohm times centimeters. And so that is sufficient for the rate purposes in STAR. you see that other detectors at CVM, for example, are looking at different glasses to work on better rates. We operate at 14 kilovolts. There's a plus and minus 7 kilovolts applied on both sides. And we have a gas mixture that involves freon and then isobutane, which is for quenching purposes. For the STAR barrel timer flight, there were more than 4,000 modules necessary. And so the Mrpc production took place at 2 sites, one at USTC and the other one at Tsinghua. You can see here some pictures from the construction, and you can see it's a little bit difficult, but you can see here a glass layer that's being held. You can see the pickup pads, and you can see here how between 2 bricks the gluing is taking place. About 30% of the Mrpcs were constructed at USTC, and Tsinghua took care of 70%. Again, for example, CBM, much of the construction took place at these sites as well. And at Tsinghua, there's indeed a lot of industry really developed around the applications of Mrpc, not only in detectors, but also in detection facilities, for example, for harbors where Mrpcs in fact are used to in scanning of containers and stuff like that. All right, the barrel timer flight detector in numbers. So the detector is segmented in these TOF trays, which replace the CTB, the central trigger barrel. What you should know is that each TPC sector basically has 5 of these trays at the end. That results then in these 120 trays in total. You can see here on the right side a picture of a tray where the eta equals 0 is on this side, and this is the eta equals 1 side. The electronics is below, and so the STAR detector or the TPC would sort of sit here. You can see that all these RPCs are more or less oriented towards towards z equals 0 in the detector. So this is that. Here, I think this is Jared and Kohei, who at UT Austin were together with quite a few others working hard on actually assembling the trays, which means putting in the modules and then mounting the electronics. This was also a unique thing, that really the detector integrated the electronics in the tray, as you can see here. The digitization and readout really was designed around CERN's HPTDC chip, and I'll talk a little bit more about that one because it does play an important role in what follows next. We have so-called T-Dig boards that have 3 of these chips. Each chip can handle 8 channels, so we have 8 T-Dig boards per tray. Kind of to put the relative scales again here, so we're talking really in terms of 23,000 channels. We have a little less than 4,000 modules in STAR, and then these digitization boards, we have a little less than 1,000, at least for the barrel timer flight, and these are all distributed across 120 trays. The installation of the barrel timer flight started in 2008, where the first 5 trays got installed and verified, and then in 2009 we actually had about 70% of the trays installed, and this is, for example, in the PP at 200 GeV, that was in 2009, the timer flight detector already actively participated. As a reference, we refer to tray IDs for those of you that are in the control room taking shifts. We have tray IDs 1 through 60 that correspond to that overlap with the TPC sectors 1 through 12 and are on the west TPC side, so that's Z, positive Z, and tray IDs 61 through 120 on the east side. In 2013, we actually have 4 trays modified so that these so-called GMT modules could get introduced, which is used for TPC calibration. I think maybe Gene at one of the junior meetings discussed that. But what it means is that I indicated here with the black dots that 4 trays were modified, and for each of these trays we removed 8 Mrpc modules, 4 at eta equals 0 and 4 at the eta equals 1 side. Okay, so on this slide you can see all these Mrpc modules hugging the TPC on the left side, and again the layout of the single BTOF tray. What I want to point out here, two things I want to point out here is that indeed in these GNT trays, we removed the first 4 here and the last 4 here. So that's where the GMTs are located for these particular 4 trays. But what I want to point out with this slide really is some coordinates that we use and that you may see in your offline analysis as well, which is the so-called local Z and local Y, which really are the coordinates of a track as it hits a module along the Z direction, which is along this side in the pickup path, which is 6 centimeters and goes from +3 to -3. And then this local Y, which is basically along the phi direction, if you look at this from a star global point of view. And also again, has for each individual pickup pad a range that is between a range that is about 3.2 centimeters. Now, like I said, these are sometimes people use cuts to on local Z or local Y in their analysis. Well, we're talking about the barrel time of flight, but actually, the barrel time of flight really, as we'll see, only provides us with a stop signal. For time of flight, you need a start and a stop to actually get a time of flight. So the TOF start detector is implemented by means of the so-called Vertex Position Detector, which is located really outside the main star detector at about 5.7 meters along the beam line, and you can see on the left side the 2 VPD detectors. It has a very forward coverage between 4.2 and 5.1, and it involves 38 converter PMT tubes, like what I show here on the right side, where you have a LED converter followed by a scintillator and followed by a photomultiplier tube that is able to operate in a strong magnetic field. So here you can see where TOF-P's photomultiplier tubes were repurposed, and they all are now showing their second life in the VPD. We have 19 channels on each side. Like I said, we have a range that's between 4.2 and 5.1. If you look at these detector layout, you can see that there's actually an inner and an outer circle. The outer circle is the one that pushes you down to 4.2, but you should keep in mind that your azimuthal coverage is something in the order of a third only, as you can tell already from the way these are spaced here. As I said, the primary offline function of the VPD is really to provide the start time for the barrel time of flight system, which by now include not only the barrel time of flight, but also the MTD and the end cap time of flight. Being able to accurately determine the timing also allows a secondary offline function, or maybe even more prominent offline function, which is an alternative measurement of the location, the Z location of the primary vertex. And often in your analysis, you'll see that you use a difference between the vertex position determined by the TPC and that of the VPD to say something about the validity of the vertex choice or vertex location. Not only that, the VPD also participates in star online triggers, and the VPD is world famous because it actually got featured in when Apple made a movie clip about 7 years ago about the fact that they existed 30 years or whatever, Macintosh 30 years. Anyway, let me not go through all that stuff. Let me just go to second 47, and it's flying by before you know it, but everybody deserves their second of fame. Here's, you see, I'm gonna hold it, get rid of the commercials, and there it is. The VPD. Okay, Bill Christie is there as well. Paul Sorensen is there as well, and they check whether the event display agrees with what they see in the TPC, which I certainly hope does not mean that the beam is on. But that's just for Apple's commercial. But there you go, the VPD featured in this video clip. Very important. All right, so let's move on. BTOF electronics. The electronics is very important here, and I'll kind of look at this more from sort of a top level view. A lot of the electronics, like I said, is really centered around this TDIC, this HPTDC chip. So each Mrpc has a board that takes care of the amplification and signal shaping, and that signal then is discriminated at this board and provided to the digital, the time to digital conversion, which is at the heart of the TDIC. These are all on the TOF tray. There is some additional CPU functionality that allows us to bring in and out things like clock and other decisions. We have for 30, group of 30 trays are hooked up into what we call the T-hub, and there are 4 T-hubs that then provide our interfaces to the trigger and to the data to STAR's data acquisition. Because it's important when you want to do start timing and stop timing, it's really important to combine both the bell time flight and the VPD. And you can see here indeed that the start detector, the VPD, is also not only using the same TDIC electronics, of course a different amplifier, because these are photomultiplier tubes that provide healthy signals. Mrpcs still very faint signals, but it's the same structure as it leaves the TDIC and enters the T-hub, and basically sits in the same data stream as the BTOF. In fact, the VPDs east and west are encoded as BTOF trays, should you ever wonder why there are 2 more trays in some of the plots that you see. They are actually the VPDs. It's important to realize that electronics also contribute to time resolutions, and so Jing Liu, a postdoc at Rice, he demonstrated here that, say, the onboard time resolution was less than 20 picoseconds. All right. So what are the timing considerations now that we have seen the Mrpcs, the electronics? What is it that we're looking at? So the timing will be based on the leading edge of this incoming Mrpc signal, and that's set by a discriminator that sits on the Tino board, close to where the Mrpcs are. We have a signal height correction, which we call slewing correction, that is based on a concept called time over threshold. In older systems, you often used an ADC to find out what the signal height is. But that would mean that in a detector like this, where you've got 23,000 TDC channels, you would also need to then design 23,000 ADC channels. And that makes it very pricey. So what was done instead is that you shape the signal that comes out of the Mrpcs, and such that you can actually do a measurement of a leading edge and the trailing edge. And you use the time between the leading edge and the trailing edge as an indication of the size of the signal. That is important because we know that there is this signal height correction that needs to be applied. And instead of the ADC, we use this time over threshold to do that. So we do, for every measurement of the Mrpc, we actually register 2 time samples. Now, that's one thing. Signal height is an important consideration in when you deal with TOF timing. The other is, of course, that none of these cables are exactly the same, and some signals travel longer than others. So there are all kinds of timing offsets that we kind of collectively group here under T0s. Cable length, like I said, is one of them. But there are also other more variable timing offsets that you can correct for, and this is what we'll soon see we refer to as hit position dependent corrections. But before we can do any or all of that, it's important to realize that the time to digital conversion that we opted for in STAR, and Elise for that matter, is one that comes with a chip that has a very large intrinsic nonlinearity. And I'll show you in a second what that means. What we see is that because of all kinds of process variations in the HPTDC chip, we see that the response of the TDC is very nonlinear and is unique for each chip, for each channel. So we need to do a channel by channel calibration first to tackle this nonlinearity. And once determined, we expect no changes, and indeed a few years into running TOF, we did some spot checks and indeed could confirm that that didn't change. All right, so the HPTDC chip is a chip that actually, after it's developed at CERN, it's CERN for use at LHC experiments, but it also got commercially sold by Cayenne. As you can see on the right side, I took this picture where they have this 32 channel, so that means that there probably are 4 HPTDC chips on this thing, that they for some time were selling commercially. We operate the HPTDC chip in this so-called very high resolution mode, where we provide an external clock that is 40 megahertz. Now, for those of you that are somewhat familiar with the LHC, that sounds familiar because that indeed is the LHC bunch clock. I know people at STAR sometimes were wondering why, how did we came up with 40 megahertz? Well, now you know it. And so this 40 megahertz external clock is what provides us the first 11-bit in a 21-bit timing information. So this gives us these course timing that its least significant bit is 25 nanoseconds, which again, for LHC aficionados should sound very familiar. And then on board of these chips, there is an internal phase lock loop that multiplies the 40 megahertz by a factor of 8 and allows us to push in another 3 bins that allow us to push that number of least significant bit from 25 nanoseconds to about 3 nanoseconds. And then subsequently there's a delayed locked loop of another 32 cells that give you another 5-bit, pushing this to 98 picoseconds. And then you have finally some internal RC delay lines that end up at this last 2 bits that really push the least significant bit to something about 25 picoseconds. We typically on a TDIG have, on a TDIG board, we have 3 of these chips. So that means that each TDIG board can cover 4 Mrpc modules, and we have 8 of these digitizer boards on the TOF tray. The problem really is in the way the nonlinearity really comes from all these internal changes, internal manipulations of that clock. And especially when you have RC tapped delay lines, you will have the effects of, as you know from electronics lab, the fact that resistors and capacitors have some production range that can easily be between 2 and 5% differences, which directly will have an effect on your timing, which you base on these RC tapped delay lines. There's also unequal bandwidth in the delay lock loop, and then we have actually seen some noise coupling from the logic network that comes in and the sampling clock network. So all in all, what you see is that these higher level tests show that we have over these 2048 2 to the power 11 bins, we see a rather strong differential nonlinearity. This plot that I show you here is a plot where we provide this TDC chip with a uniformly random distribution with respect to the TDC clock. So by all means, if you run this for a long time, you would expect this to be a flat distribution, and that's most definitely not what you see. You can see that there is quite some range in what you do, what it gives you back. I think somebody's injecting a keyboard, but all right. Let me continue. What you see, you can use this clearly the fact that some bins get more entries, in other words, are wider in time than others, as a way to calculate what that nonlinearity is. And this so-called integral nonlinearity is a calibration that we apply and that you can see here on the right side. What you see is that if you do not apply that nonlinearity, you have an RMS of almost 4 bins, which again, with a bin being typically in the order of 25 picoseconds, is way too large and really kind of smears your data quite a bit. So these INL corrections need to be applied, and this right plot here shows you that the corrections that actually are substantial, if you look at that, and really differ for each channel, and this is just for one channel, but differ for each bin a lot, you need to apply this. So we have this this large database that for each of the 23,000 channels, we provided with this particular response function of the TDC. And that is a significant database that, for those that once in a while run on raw DAC data, this is one of the things that takes a little bit to load at the start of an analysis, of a production. But it's worth it because, there you go, if you apply the INL, you can indeed see that your time resolution can drop from about 4 bins to to about 3/4 of a bin. Okay, so let me do a quick time of flight recap. We need a start and a stop time. The start time is the VPD, the stop time is the barrel. We benefit from the fact that both systems use the same electronics. They run off the same free clock. And we have this raw timing information that will be the timestamps that we use. In my undergraduate lab, right now, in fact, my students are using this nice little time calibrator. That's very old school. It's in a NIM rack to do their calibrations. We, in what follows next, need to do some other ways, more data-driven ways in which we will do the calibration. For the VPD and for the barrel time of flight, there are slewing and T0 corrections. And as I already mentioned, for the BTOF, there are some additional hit position dependent corrections, as well as an alignment that needs to take place between the TOF and the TPC. So signal height corrections, I show you this plot on the right side. So you see that the time of a threshold, really this time that the signal is below a particular threshold, is somewhat proportional to the size of the signal. This larger signal clearly has a larger time of a threshold. And that's what we use in the calibrations. That is what anybody uses in any time of flight type of calibration. The other one that I want to highlight here is this signal propagation correction that you also might have heard of in terms of local Z. And it's important because when in the early prototype test, we saw that there is about 40 to 50 picoseconds per centimeter that this signal travels from wherever it's generated to where it's being picked up by the leads that then go into the amplification. If you don't account for that spread, then with 6 centimeters, you're looking at smearing that easily can be 200 or more picoseconds, something you want to avoid because remember, one of the first slides that I showed you were about time resolutions of 100 picoseconds. This already kind of would spoil that quite a bit. So this local Z information is something that really has to come from accurately extrapolating TPC tracks to the time of flight detector. And what you'll see is that once you correct this signal height correction, you then apply that to your signals. You do the signal propagation correction, then you apply that to signals. You can see that this actually is something that you probably will need to do in several iterations. And indeed, we see that easily 5-6 iterations are necessary to have this converge to stable results. The VPD calibrations, as that provides not only the start time but also the vertex position, also involve a few steps that I highlight here. For one thing, each of these VPD channels have their own cable lengths and what you have. So one thing that you need to do first is remove all these quite substantial, I mean this is a nanoscale scale, to remove all these different offsets and make sure that they all are at the same, that the leading edges are all at the same time. You need to then do, again, this leading edge, the slewing correction. You can see here that if you don't correct for this, again, look at the scale, nanoseconds, that for smaller signals, they really come in substantially later than they should. And so once you correct this, you can see that as a function of the time of a threshold, the signal height, you don't see any changes in the leading edge timing. And then you need to make it such that the VPD timing, if between east and west, agrees such that if you look at the TPC vertex, that they are both, the difference is at 0. That's basically just a T0 correction that's being applied. If you look at this resolution that you often see in these kind of plots, you can see that indeed something in the order of half a centimeter would be something like 15 picoseconds, and presuming that, and this is gold on gold in 114, that all tubes contribute in this measurement, you see that typically an average VPD resolution per tube is in the order of 85 picoseconds. The VPD really shines because, especially in heavy ion collisions, you have a lot of tubes participate. So then the effective time resolution of the VPD, the overall, quickly drops. And I already mentioned, in heavy ion collisions, this is all well. The VPD response highly depends on the collision system, on the beam energy, or even on solid changes that following a recabling, just unrolling cables and rolling them back. We've seen that this actually has an effect on the VPD resolution, on the VPD response, I should say. And this does mean that for every run, we will need to do a new calibration or need to update calibration if we know that during a run changes in both have happened. So the VPD calibration is an unavoidable thing. The other thing about the VPD that you should be aware of is that because it's at a fixed location and thus at a fixed eta range, the efficiency will depend on the beam energy. And that means that if you take these URQMD simulations that Bill Loeb did a few years back, you can see that the eta distribution here on the left side for 200 GeV, and then he did several more for lower energies down to 5. Okay, this plot is there's a lot of stuff on it. But if you look at the right plot, you can see that within the range between these two red lines of the VPD coverage, that as your energy starts to drop, that the beam rapidity in magenta slowly but certainly starts to move out of the acceptance of your detector, as does the spectator, so the typical eta range of the spectators that starts to move out, and you see that the type of physics that the VPD is responding to is changing as a function of the energy of the system. On the right side, you can see that this basically has an effect on the efficiency of the VPD, the efficiency per event here, as you go to lower and lower square root of S. So you can see that if you barely have 1 and 1 on each side of VPD, then starting below 39 GeV, it's becoming, the VPD efficiency is really starting to take a significant drop. That is why in beam energy scan analysis and in production, we are not using the VPD anymore as a start time, but rather use a concept called startless timing, or bootstrapping the beat off itself, and we'll discuss that a little bit more later. Knowing what the location of the TPC track on an Mrpc module is important. I mentioned that earlier. That means that the alignment of the barrel timer flight with respect to the TPC is important. And so while we have an ideal geometry that we put in the reconstruction, we actually use, again, a data-driven way by looking at the location of the Y local and the Z local for all the matches. And you can see this kind of wily pattern, both in Y local and Z local, that tell you that clearly we have a detector that seems to be not particularly well aligned with the TPC. So using these offsets, we can realign the trace, and as a result, see that after realignment, our Y local is flat, our Z local is flat. You would think that this is just a one-time thing because the TPC is mounted on the TPC on the rails, but we do know that in the TPC calibration, at least in the past, some realignment of the sectors was done, and so we on the time of flight side we're a little bit on the receiving end. So for every run, we repeat this alignment. It's a quick and simple check to make sure that we are and still seeing these flat lines. All right, moving on. So the beat off calibration, the way we do that is we select actually a very pure TPC sample that we know are pions, very specific momentum range, a DEDX range, and good tracks. And then we align our time measurements such that the 1/beta that we measure agrees with the 1/beta that we expect for a pion with that particular momentum. And we do that for the time of threshold-based slewing and the local Z. And again, as I said before, this is something that will be repeating and iterating several times to converge. But again, here you can see of an example where the time of a threshold dependence, the slewing correction, is corrected for. Here you can see a plot of the local Z where, again, there you have something in the order of 200 picoseconds almost between where the pickup is and where the other end of the Mrpc is. And these are all distributions that we like to see straight so that there's no dependence on that. And then there are other T0 alignments that I show here. Here is the fact that a signal, once it's created, it still has to travel, if it's on the ADA 0 side, so in the center of the detector, that signal still has to travel all the way to the end of the detector electrically through all kinds of, you have the T-ditch, then it goes over cable to the TCPU. That all takes time, and you can actually see, if you look carefully in this plot here, you can see the 4 T-digits. We actually have T-digits in 2 groups. So you got one set of groups here, and then the other one, you can see that indeed they all take a little bit longer to bring this. Again, these are T0 changes that we want to flatten out. All right. Now the challenge in all these kind of things is that we need a lot of batches per cell. The cell is small, so that means that we need a lot of statistics, which typically means that we do these calibrations when we have access to large gold-on-gold data sets. And this table on the right side, the only thing that I want you to take away from that is that if you would do calibrations on PP collisions, then just because of the multiplicity being low, if you want to do that on a channel by channel, you basically need to use all the data. Whereas if you were able to just use 200 GeV gold-gold, then you can do your calibration with little over 1 million, which is great. There is some silver lining though, and that is that the barrel time of flight calibrations, contrary to the VPD, do not depend that much on the collision system or the energy. It's electronics corrections that we take, that we correct for, and the barrel time of flight is not removed, or less it is, but no. The trays are just in place, so there's no changes here. That means that we actually, and we have shown that that can be done, we can reuse prior calibration data sets, which means that if we have a data set that, or calibration that really was done with a lot of good central high energy heavy ion data, we can actually use those corrections then for data sets that have much lower multiplicity. We don't need to recalibrate anymore. Well, not recalibrate is a little bit, if there is particular detector maintenance, then of course such a tray may need to be recalibrated. Right now, for example, we refreshed our current data calibrations based on the heavy ion on the isobar running of 2018. So that's a really well and good refreshed calibration set right there for B-Man scan phase 2. Still, alignment and T0s need to be done, and I show you here a picture that was something that popped up earlier in this run, where one of the T-hubs was repaired, and as a result, that whole timing was shifted, something that got recently corrected for. I'm going to skip this slide, just mention that here's the TOF analysis layout, where you can see all the steps from the data that you get to the PQDSD or the Microdsd in this slide that ends up at your desk. There's a similar trajectory in the simulations. This is basically what the layout is. Again, I'm going to skip that in view of time. So what is the data that you have in your Microdsd? Well, in the Microdsd, we see the beat of raw hits, which is very useful for any reanalysis purposes. We have the beat of hits, and just to be clear, that's not only the beat of, but also the VPD hits. Remember, trace 121 and 122. And these are the physical hits that are really have the leading edge and the trailing edge combined. The timing is not necessarily yet fully calibrated, although the beat of hits could get that timing information. And then it has, for the tray hits, indexes to what the associated tracks are. In the header, we keep a lot of calibrated VPD information that includes the vertex position according to the VPD. As well as information that is important for startless, like the number of particles that were used to bootstrap the beat off in determining its own start time. The beat off PID trace is really what matters the most for your analysis, and this is for a significant part. All the stuff that I highlighted in blue is what is available in the PQDSDs as well. So there's matching information, what the cell ID is, what the match flag is, which is a indication of whether there is a TOF match. Well, if there's 0, then clearly there's known. Whether it's 1, that means that actually a single track hit one of the Mrpcs. And then there's this option, or not option, this flag value 2 and 3, which indicates that a TPC track hit multiple cells. And so to select the best one, we either, or first I should say, look at which of the 2 cells has the lowest time of a threshold, the idea being that corrections are less for large time of thresholds. So if we find one that is the largest, we pick that one. And if that is still a decision that doesn't come to a conclusion, then we look at the local Z correction and make sure that we select the cell that has the most optimal local Z value. So that's really what the magic is of 2 and 3. Okay, so that's what you have in your Microdsds and by extension in your PQDSDs. I'm gonna I'm going to wrap up shortly, and I want to really highlight here. I mean, I can talk about startless mode, but I really want to highlight some of the great work done by a couple of juniors here, by Ben and by Bassam, who actually have further investigated this so-called beat-off startless mode, where we use tracks in the beat-off, use DEDX information to find out again whether they are pions, and use that then as a way to find out what the common start is. And that's a view of a VPD that's not operating efficiently, especially at the lower beam energies. I am highlighting here both Ben and Bassam's work because they, in the last couple of months, I would say, have done a great job in further optimizing this startless method. For example, Ben has done very interesting work in extending the set of particles that are used to bootstrap the beat-off in providing its own start time. It was earlier only limited to pions, but especially in fixed target, that was not very efficient. Keep in mind that the acceptance of the barrel time of flight almost gets halved. Here he looked at extensions that were done by including the protons, and actually went one step further by further optimizing the selection, and that actually is looking very promising for fixed target. In fact, this looks very promising just to implement for any type of system, regardless if it's fixed target or not. Bassam took this even a step further. He has been working hard on seeing the startless work in not fixed target, but rather in PP and PA collisions, and not only that, but also mixing in those events that, albeit less efficient, involve a VPD. So this is quite exciting, and there's still some work in progress, but this is something that I think we'll soon see implemented in the startless timing for BMAScan phase 2. Bassam here also lists how, if you don't have it, how you can sort of, in your Microdsd, include startless. Again, in production, this is all done for energies below 39 GeV, but if you want to play with it a little bit more, here are some really nice instructions on how to expand your macro to do so in this so-called afterburner mode. Okay, one last example of how the time of flight is in your showing up in your analysis. Matching efficiencies. Most of the time people rely on this data-driven method. I show here an analysis that Daniel Brandenburg has done for this BMAScan RCP paper, and where you indeed look at the denominator TPC tracks, and then in the numerator you look at the tough match tracks, and you can see here some data-driven plots of the matching efficiency. What has been happening meanwhile, and that takes me to my last slide before wrapping up, are some very interesting developments that have now a so-called beat-off mixer maker be part of production that allows you to actually ask for beat-off to be included in embedding. More recently, we actually fed back some of the calibration workflow, specifically the resolutions, the time resolutions of each of these 23,000 channels, back into the beat-off calib maker and back into, into the simulation maker, so that the simulation maker can actually smear with realistic cell-by-cell time resolutions, which should have a very beneficial effect on using the beat-off in simulations and thus in the mixer maker. I already pointed out, and I put a link here for those of you that are looking at the PDF file, the improvements that Bassam has been rolling out that improve the outlier rejection in startless mode for the beat-off and the VPD, that really will see improvements in PP, PA, but actually, again, if it's good for PP and PA, it's good for AA. So I'm very excited to see these optimizations get into the library soon. Similarly, as I mentioned, Ben has looked at updating the start list for the fixed target. And again, here, the same story. If it's good for fixed target, it should be good for a collider mode data as well. So here, again, these are updates that we soon will see rolled out for our BMScan phase 2 production. So I encourage you to take a look at these. You should definitely be excited about what, at least what they have been working on. I like that a lot. Another thing to make it easier for analyzers to use the time of flight information is that, again, thanks to this updating the calibration workflow to give us cell-by-cell time resolutions, we updated the NTOF sigma variables that are in the Microdsd, and thanks to Grigory now also in Dev, at least in the PicoDSDs, where we normalize this 1 over beta expected minus 1 over beta measured by a realistic time resolution for each cell. And that means that you can now use this NTOF sigma and greatly simplify the use of TOF PID by requiring NTOF sigma to be less than 1 in a similar fashion as you've done, as you do for the EDX. And so I'm only here pointing out to some recent QA board report that Sheng Liang produced last Friday, where you can see for the first time that in fast offline, you can see NTOF sigma used to identify particles. So all in all, these are great and timely updates to improve the PID for the upcoming BMScan phase 2 productions, and I'm very interested in seeing those soon in the libraries. So looking back and then looking forward, this StarTOF project has been 20 years, more than 20 years of many efforts by many people, and I took a lot of plots and pictures of many people that I tried to list here, and this is a list that is terribly incomplete. But I think that we can see that even after 20 years, there's still exciting new developments to improve this TOF-based PID, especially in PP, PA, and fixed target. So that said, I also expect that we will see a lot more excitement to come with forward time of flight based PID from the ETOF detector. And with that, I conclude my talk and love to hear some questions. Thanks, everybody.
So I see there is a first question already. Wrong. Go ahead.
Yeah, so Frank, thanks for the very nice talk. So in one of the slides, you show the TOF matching efficiency, which is much lower in central compared to the peripheral events. So what's driving that?
I must say that I think we've wait, let me see.
Yeah, here.
Well, I mean the time of flight detector is the size of the cells is done to I mean you get occupancy effects. So I think this is what really drives that dropping if you go to higher multiplicities.
So by that, so you talk about, say, if I have one track matched to multiple cells, then you kind of choose the one that you think is the best?
No, this is not that. This is when you have two tracks that are pointing to the same cell.
And
those
you reject them? Okay, so you only allowed, you don't allow that cases to happen.
Because you don't know which of the two tracks really is the one that's giving your timing signal. You could, if you want, push this a little bit more and be a little bit more clever about it, and bring some, I mean, I can imagine that if you look at seeing what the potential possibility is that one or the other track makes more sense. But in the matching algorithms, these are typically tossed out.
Mm-hmm. Yeah, since I'm talking, can I just ask? So here, so the plateau is like in center is 56, in peripheral is like 59. I usually hear like the patching efficiency should be around like 65, 67%. Is that what I should expect, or 50, or like high 50s is what we expect?
It depends on what your, I mean, that's why I put the criteria that Daniel used in his analysis on the left side. It strongly depends on what you put, for example, the numerator. If you put any stringent cuts on Y local and Z local, you effectively are reducing the matching efficiency. So it's in order to say something conclusive about comparing it, we should really compare what went into the other plots that show matching efficiencies. It's data driven, but it also depends on what the analysis is and what the parameters are that go into your analysis.
Okay, I see. Thank you.
I had a question about the technical design for the Mrpcs.
Yeah.
On the slide that you showed, the different layers. So
Yeah.
those glass panels are held in place mechanically?
Yes.
Okay.
So you're talking about the last ones. The outer glass plates are held together mechanically, like what you can see here.
But what about those inner glass plates?
They are held together by the fishing line spaces, which are external. I don't have a plot. I don't have a picture here, but let me see if I can see it from these pictures. No, I don't. Across, not completely across, but between the glass plates, between the inner glass plates, we actually run a very thin fishing line. And that is what keeps the plates separated at the 220 micron level. And I think, I mean, I'm sure what else you mean. I mean, the spaces.
Yeah, that's good enough. Yeah,
Yeah.
I couldn't put in the pictures, but that makes sense that now. And their floating potential, so the field in the glass is being induced from the external field of the cathode and anode.
Yeah. Well, so the electrode here, this is the black line. That's the graphite at which we bring the +7 and the other side the -7 kilovolts. The pickup pads where we pick up so basically your anode and cathode are the outer glass plates, if you want. The pickup pads are in red, so these are the ones where we actually pick up by induction the signal that is then hooked into. Yeah, you can see on the right plot here, you can see these, it's maybe very difficult to see, but since everybody is probably looking at their own screen, they can zoom in. You can see all these little twisted cables coming out. These are the 6 signal leads that come out of it.
Okay, but for the floating glass plates,
Yeah.
the voltage on that is because you said it goes to -2 volt, -4 volt, and so on.
Mm-hmm.
And so that voltage is being induced from the external field?
No, this it's not induced. I mean, they will electrostatically at some point take on these voltages because you apply you have this electrical field that you have between so not electrodes, between the graphite layers here. But they will at a later stage, because you got this current flowing here, albeit with the large resistivity that these plates have, this becomes a equilibrium, and which helps in really keeping these voltages at the exact portions as you can see here. So these detectors, it's not a detector that you can just switch on right away. They will, if you ramp them up, then shortly after they're ramped up, they are operational. But it takes them a little bit of time.
Oh, once the charges pass through, it will induce that voltage until it comes to equilibrium, essentially.
Yeah, because keep in mind, right? I mean, so if these are all these glass plates, the charge, if this is the cathode, so here the charge that will seep into the resistive plate here, there is certainly also a positive charge that moves up here. So in the end, these plates will get in a steady state, and you get
Okay.
your
All right, thanks.
Okay, so do you have any more questions?
Oh, Frank, I have one more question. Just this slide, and the slide 10, yes. And we have one track, but in the plot we have two signal electrode. Well, that's understandable, but we have one track, so we need one signal. How do we combine these two signal electrode together to get the signal we want?
well, you got your electrodes and you look at the differential between these two.
And so what we can get from the differential?
From the differential, you get the total charge that is induced on your electrodes from a charged particle passing through a gaseous detector.
So from these two signals, we can get the particles charge.
Not the particle's charge, you get the I mean, for the Mrpc, what you get is just the fact that this signal that you have a charged particle passing through it, so you get a signal. Not very different, I would say, from what the mechanism is in a TPC detector. I'm trying to understand what your question is.
Yeah, because we have two pickup pad. You for the left plot, you draw two pickup pad. Here, one is cathode, one is cathode, one is anode. So when the track goes through these two pickup pad, it will give us two signals like you draw, right?
You measure one signal.
We get one signal.
Yes.
Okay.
You look at
but when the track goes through each pad, it will produce like electrically they will produce a signal, right?
yes, yeah.
And then it will go to the Mrpc. They will combine to one signal, right?
I'm sorry. Could you repeat that? I wasn't clear what you just.
What a track goes through a condition like the left plot.
Yeah.
So it will produce two signals for the uphead and the
No,
lower.
it produces one signal. It's just, I mean, you look at the signal that you get on your anode. You look at what the charge is.
Okay. Well, because I'm considering these two. Okay, 1 second. Okay.
It's a very, very small, it's a sort of in the lower 10 picocoulomb kind of charges that you will be picking up at your electrodes. Let me discuss that with you, Yeding, after the
Yeah. Sorry.
Actually, I had a question. So this is really exciting that the news that you mentioned about the bit-off mixer being available, and I guess the simulator as well for the timing information of bit-off. And then, well, how ready is this for, say, is this only bit-offless, or sorry, startless TOF analysis could use, or is there some provisions for VPD?
That's a good question. So I need to take another good look at what exactly the VPD sim maker is picking up. The point, though, is that the beat of mix. Let me get it back to you with an answer on that. I don't have it. I don't want to speculate on what's in there or not.
So you imply that it might not be quite ready?
Well, I mean, for getting in heavy ion collisions, you should be okay. Like I said, I cannot speculate on whether the VPD sim maker is set up. I don't think it is. So the VPD mixer maker, a bit-off mixer maker is probably only, I would think, for self-starting Mrpc scan analysis. It should be okay. But again, like I said, I mean, I will need to take a look at what the implementations exactly are.
Okay, thank you.